Hey, welcome back, kiddos. Today we're going to talk about something called electrolysis. Now, electrolysis is, well, kind of sort of the opposite of a voltaic cell or battery. Batteries or voltaic cells involve spontaneous reactions. When we perform electrolysis, we are dealing with non-spontaneous reactions. So that means we have to continually add energy for that reaction to move forward. So we will use electrical energy to bring about a chemical reaction. An electrochemical cell in which electrolysis occurs is called an electrolytic cell instead of a voltaic cell. For example, when a battery is recharged, it's acting as an electrolytic cell, not a voltaic cell. The key here is when that battery is being recharged, we're going in the opposite direction. Here, let me give you the classic example that we had talked about in an earlier video. We know that in a zinc-copper voltaic cell, that reaction is spontaneous. Let me write down the pertinent reactions here. We have copper 2+ gaining 2 electrons to become copper metal. Now the reduction potential for that reaction is a positive 0.342 volts. The other reaction has to be an oxidation reaction, and that is zinc metal becoming zinc 2+ and 2 electrons. Now the oxidation potential for that reaction is a positive 0.762 volts. Now, when we add these equations together, we get a nice, pretty redox reactions. The electrons gained are canceled out by those that are lost. We can add these potentials together. We get a 4, 0, 1.1. Okay, so we get a positive 1.10 volts. That positive sign tells me that that reaction occurs spontaneously. So the electrons lost by the zinc electrode will spontaneously flow towards the copper electrode without me doing anything. In fact, that reaction will continue until I run out of reactant. For instance, remember, this zinc electrode is slowly dissolving. It's producing zinc 2+ ions, and the concentration of zinc 2+ in that zinc cell is increasing as my zinc electrode is being oxidized and forming zinc 2+ ions. Now on the other side, my copper electrode is becoming more massive. Remember, there are copper 2+ ions in solution. They are gaining those electrons lost by zinc, and that copper electrode is increasing in mass, and the copper 2+ concentration is slowly decreasing. Now you can see, as I run this battery over time, I'm eventually going to run out of zinc metal, aren't I? And I'm eventually going to run out of copper ions in this solution. So the battery will die. It will no longer have reactants that are available to produce this spontaneous reaction or to produce this voltage. Now, let's say we want to recharge that battery. In order to do that, we're going to have to make the electrons go in the opposite direction. In other words, we're going to have to reverse this process in my voltaic cell. So what was going to happen is my copper is going to have to turn into copper 2+ ions to replenish those. And those 2 electrons will have to go towards the zinc cell, where zinc ions can gain those 2 electrons and become zinc metal. Now, the oxidation process for copper would be a negative 0.342 volts, and the reduction process for my zinc ions would be a negative 0.762 volts. When I add these potentials together, I get a negative 1.104 volts, and that negative sign tells me that that reaction is not spontaneous. In order for that to happen, I have to continually add energy to push those electrons against the direction that they spontaneously would like to flow. So what would be happening in an electrolytic cell is these copper 2 plus ions would be being produced. My copper metal would be losing electrons, and they would be moving away from the copper metal, and they would be going towards the zinc electrode where they would be gained. Now, if the zinc electrode is gaining electrons, zinc 2 positive ions can now deposit as solid zinc metal back onto that zinc electrode. So over time, the concentration of copper 2 pluses will increase, and the size of my zinc electrode, the mass of my zinc electrode, will also increase, in essence, recharging my battery. The difference here is that I need a voltage source to push those electrons away from where they spontaneously want to go. I need to add energy. Think about recharging your cell phone battery. You have to plug it in, don't you? You have to have a voltage source to push the electrons back in a direction that they don't spontaneously want to go. Of course, when you unplug it, then you have the spontaneous reaction of your voltaic cell, of your battery, and that can operate your phone spontaneously until you're running out of reactants. And then at the end of the day, you plug it back in and you repeat the process over and over and over again. You are recharging your battery. So a voltaic cell is a spontaneous reaction. It happens without us continually having to add energy. And an electrolytic cell, kiddos, is a non-spontaneous reaction. In order for it to occur, we have to continually add energy. We have to add a voltage source to push those electrons in a direction where they don't spontaneously want to go. Here, let me give you another example. If we wanted to make some silverware, real expensive silverware, it's not solid silver. The fork you use and the knife you use is not solid silver. So silver is just too malleable of a metal to use for that purpose. So we usually have a steel type of spoon or fork or knife, and we plate a thin coating of silver metal onto that utensil. Now, the process whereby silver is oxidized requires negative voltage. So the oxidation potential of this is 0.800 volts. That is non-spontaneous. What we want to do is take silver metal and turn it into silver ions. So we're going to have to pull electrons away from that silver electrode. And then what we want to do is deposit them onto the utensil that we're plating. And what will happen is the silver ions that we've produced will now gain an electron and become silver metal and deposit themselves on that fork. So we can go from silver metal on my electrode here, the anode here, the one that's losing electrons, and we will produce silver ions, which will end up depositing themselves on the utensil because the utensil we're pushing electrons onto that utensil, and that will be reduced at my cathode. So over time, we will be able to plate this fork with a thin coating of silver. It's called electroplating. Perhaps you've heard of it before. This process is also used in metal refining. When copper is refined, for instance, they will take an anode that might be 99% pure copper, and they will have some type of graphite plate, a cathode, which they will dump electrons onto. They will oxidize the 99% pure copper into copper ions, and they will migrate to that cathode, and they will slowly deposit on that cathode. And we can change the purity from 99% to 99.999%. And the impurities in that process end up falling to the bottom of the electrolytic cell. We call them impurities, but oftentimes they contain precious metals. And those can be removed and further refined to separate them into gold and platinum and such. But this is a very common process. You've used it yourself with your telephones. You've used perhaps utensils or jewelry, which has been electroplated. And the copper that we use in all of our electrical components has to have a purity of above 99.99% in order for it to be useful in those products. All right, just a short video today to go over the process of electrolysis for you. Hope that gives you just a basic understanding. We'll continue next time and we'll quantify this. We get to do some math with it. So we'll see you soon. Bye-bye.